All right, Euler's method. Euler's method is another way of approximating solutions based on differential equations. And basically the idea is that we are taking a point, approximating it as a straight line tangent, getting a next point, and getting a tangent line from that point, getting a next point, getting a tangent line from there, and building out a curve in that way. And so we're not going to get the exact curve, but we're going to get kind of approximate, and we're going to have our estimated values along the way. As we do that, we are looking at this step value h. How far do we want to go? We can have a step value that's really big or that's really small. Obviously, the smaller h is, the more accurate our curve is going to be. But what we do is we look at this x sub 0 and y sub 0 to come up with values. So we take our first values, x0, y0, and we see, okay, with this slope that's there, we're going to go over, we're going to change x by h, and we're going to go up by h times the derivative at that point. And then to get from x1 to x2, we're going to go over by h and go up by multiplying that. So it comes down to setting our original values, x0, y0. Those are our starting values. Start point. And then we have h, which is our increment. And so we would say that x1 equals h plus x0, and in general, xn equals xn minus 1 plus h, and y1 equals y0 plus h times f of x0, y0. In other words, we plug in our x0 and y0 values into our differential equation to get our y prime, multiply that by the step. So it's the slope times the distance we traveled, that gets our change in y. And then again, we can give the general idea that y sub n is y sub n minus 1 plus h times f of xn minus 1 yn minus 1. And that is our formula that we're going to use. So we want to use Euler's method to approximate the particular solution of the differential equation y prime equals x minus y passing through 0, 1, and we're going to use a step of h equals 0.2. So let's just start out, and we're going to make a table of, let's go with n, x, n, yn. So when n is 0, we get x of 0, y of 1. When n is 1, remember, xn equals xn minus 1 plus h, and yn equals yn minus 1 plus h times f of xn minus 1 yn minus 1. So x1 is just x0, 0 plus 0.2, so this is 0.2. x2 is 0.4. x3 is 0.6. And we're performing 3 iterations, so we can stop there. So then, what is y1? Well, y1 equals y0 plus h times f of xn minus 1, yn minus 1. Well, f is this x minus y. So we have 0 minus 1. And so y1 equals 1 minus 0.2 equals 0.8. y2 equals y1, 0.8, plus h times x1, which was 0.2, minus y1, which was 0.8. Oh, no, I'm sorry. Yeah. Yes, because our function is x minus y, so x minus y. And so we get y2 is 0.8 plus, this is negative 0.6 times 0.2 is negative 0.12. So y2 is 0.68. All right, let's go the next step, y3. Why don't you pause the video and see if you can work out y3 properly. Okay.
Y3 is y2 plus 0.2 times x2, which is 0.4, minus y2, which is 0.68. And so we get 0.68 plus 0.2 times negative 0.28. So that is 0.68 minus 0.056. So we get 0.624.
And there we go. There's our 3 iterations. Oh, wonderful. And then the next one says, get the value for 0.8, which means we really need to go to a 4th iteration. X is 0.8, so to get y of 0.8, we're going to do one step further, and we're going to say that y4 is 0.624 plus 0.2 times 0.6 minus 0.624. So we get 0.624, that was a point there, minus 0.2 times 0.024, which is 0.624 minus 0.0048. And so y of 0.8 we can approximate to be 0.6. That 4 borrows from there. So 6192 would be our approximate for the value of y of 0.8. So again, to get each iteration, to get our new x value, we're just adding h each time. To get our new y value, we are looking at our old y value plus h times f of x, our last x and our last y. F of x n minus 1, y n minus 1. We did x minus y because our function is y prime is x minus y. So that's the big F is y prime. So there you go.